Hello everyone. So we are going to do lab 6 today, um, which has been integrated into the IOLab system. Okay, so I have already opened the screen, the application software. Let's start by we are in lab 6. Like what I'm doing, these videos are instructional video. Okay, I'm not giving you the whole answers. I'm just guiding you how to do the lab. What can you expect in the graphs and the concept behind the lab. Okay, those will be there. Okay, so we are doing lab 6 today. Okay, start by let's put in the dongle. Let me show you what you have been doing with the dongle, the USB port like me. Try by putting the dongle into the computer, into the laptop, into Mac. Okay, so we can start by write your name, your group member's name. Okay, then you can move forward, writing your name. You can click on save and go next after that. Do not forget this step. Okay, and yeah, go ahead, you can read these things. Yeah, Newton's first laws of motion, this is first law, this is second law. You can read those things. Okay, okay, you can go ahead and read and make your predictions. Yeah, so they are asking you if you throw a clay ball or bouncy ball to a closer to close the door from a distance. Okay, if you want to close the door from the distance, which ball you will throw, like the one that generates more momentum will more impulse will create the door, like will make the door to close. Okay, that will be effective in closing the door. So you can go ahead and read, make the predictions. I've already said the one that creates more impulse will help to close the door. Make a prediction and click on save and go next. Okay, do not forget that. Okay, in the next slide we will use our lab. Yeah, so we have to click it on first thing. Let's click it on. That is weird. Now we have to use the plate like thing so that we can wait by putting the balls. Okay, this thing, so it comes with the lab itself. You can scroll it in here. Okay, okay, and you need bouncy balls, like small clay balls. Okay, you can, once you have the clay you can, okay, should I keep it somewhere here would be fine. Okay, no, let's keep it here for now. I don't need now. Okay, insert the, we did that. Yeah, put the place the IOLab so that the force sensor is on top. Force sensor is on top means the force sensor is right here, that's on the top. Okay, and then separate the clay into a small piece. Make your clay and medium piece very smaller weight as the bouncy ball. So we'll make one as a very as one as bouncy ball, and I think we can make one double and much larger, so we can make three of them. Be sure to zero the force sensor with nothing on plate by clicking the zero sensor before each measurement. So they want us to measure the bouncy ball, medium clay, and the large clay. Okay, so I'll show you. Then okay, let's start by measuring our weight of our bouncy ball and clay balls. So usually what I have seen, like people are having trouble doing the re-zero sensor. Okay, zeroing the sensor. So I'll give you a trick that should work in every, whenever you have to re-zero thing. Okay, so let me, so what you can do is when there is nothing on the laptop, yeah, there is nothing right now here. So what you can do, you can just measure it, record it. Okay, you see there will be something. Yeah, so that value is supposed to be zero. After you see this, you have this thing, you can just click on re-zero sensor. That's it, do it. Okay, once you do this one, then you may remove and then just click on re-zero sensor, and then you are good to go to measure. Okay, so let's start with our bouncy ball to measure. Okay, it's weight, so you can keep it on. After reserving the sensor, you can keep it on the top. I know it would be difficult to keep on the top. In that case, you can use just a small sticky clay. Okay, and put it in the there or in to the ball, and then attach that with this one. Okay, so that you can weight it. Okay, and then you can click on rec record. Yeah, that should be okay. Okay. Okay, so that's one for the first one. You might see those lines, that's fine because you see the range is not that high. If you want to make it look good, you can adjust your range like from 2 to 2 auto scale, that's thing, okay, but that's fine. Previous was also fine. And then, okay, then this is done. After that, we need to wait. Okay, so if we click on regional sensor, if you get error, that could be a problem. Okay, so what I suggest before measuring the next one, you can click on, there's nothing right now, yeah, you can add on, okay, just click on record something, okay, let it, it's zero right now. I think we don't need to worry about it. It's already zero. Yeah, in there, if you want to just make sure, then you can click on zero sensor again. Right now, there is nothing. Yeah, okay, so we don't need the second one we used for zero sensor. Remove. Okay, and then we can click on zero sensor. Then we can wait our clay ball now, like medium sized clay ball, similar. I have made it okay, similar to the weight of the bouncy ball. And click on record. It's like it's not that fixed. Weight has to be fixed, but don't take it too high also, okay, because it might, it's not good for the IOLab also. You might use different bouncy ball, okay, different size of clay record. Okay, let's measure this weight, kind of similar, yeah. If it's not same also, like we can take, that's fine, some deviation is okay. 0 0.05, 0 0.07, that's okay. Or clay, you can, if it is clay, we can add the clay, yeah, and you can always add the clay. Okay, so if this is lower, okay, let me do it again. Or that's just a trick. So okay, let me remove this one again. There is, right now there is nothing here. If you want to read zero, it has been suggested to read zero sensor directly also, but to be on the safer side, because I have seen people selecting this one and doing read zero sensor, that would create a problem. Without keeping anything here, just record something by adding on also, you can do that. Right now it's zero, that's fine. If and then click read zero sensor, okay, and then you can remove the one that you use for read zero, and then if you click read zero sensor, that will not be a problem. So it again, okay, and then record it, kind of similar. Okay, we can take that, it's fine, 0.55, or you can add it to make it exactly same also, okay. Okay, you can do that actually, increase the weight of the clay ball and put it, I'm just giving a hint, okay, so that it will be equal to the, you see it's kind of little bit low, yeah, this part is for, what's that, this is for the clay ball, that was for bouncy ball, so you can try to make it as close as possible, that's fine, okay. And then to the next one also, okay, you can just add on, okay, I got something, it's in zero, that's fine, but if it's not, you can just always click on the zero sensor and you the one that you used to record. If there is right now nothing, click on zero sensor. Let's measure the heavier weight ball, okay, so you can keep it here and click on record. It should be okay, 0.1, kind of double, yeah, so we can take that. And yeah, so after that, once you have waited, so you know how to take the average now, yeah, you have come so far, so you can click on this thing, okay. If you want to make it look good, as I have already said, like it's, small fluctuation is okay, so it doesn't matter, okay. So it's kind of, so what you can do is you can put auto scale, and seeing your range, you can just, or if we can make it 1 to 1 also, yeah, 0 0.05 also. So seeing your value, you can set the auto scale, and that should be fine. Okay, so you have 3 values here, yeah, kind of same, and then you can do the average thing, click here, select the region, kind of more whole, so you can see, you can increase the weight of the clay, small clay also, to make it look around 0 0.06 also, okay, but you can, okay, it's kind of double, that's okay. Or you can, if you want to make it, you can always play with the weights, yeah, increase, decrease for the clay ball, it doesn't matter, yeah, the size of the clay ball, so that we can match the weight. So because it has been said here somewhere, a medium piece, well, it's medium smaller clay is very similar to the weight of the bouncy ball, and next one is much larger piece, okay. And they write your average value is there, okay, you can do your, if you have larger value of the weights, and while doing auto scale, if you keep 0 0.5, 0 0.5, you might not see the graph, okay. So based on this, you can do the auto scale, you don't need to do also, if you don't, But if you want to do auto scale, so I just saw my value was around 0.06, 0.1. Okay, that's why I 0.06, 0.1. That's why I kept auto scale from 0 up to 0.5 only maximum. If you have 0.5 6 word, then you might need to do you might need to auto scale in different range. But usually we don't use that higher weight. Yeah. Okay, so go ahead to rewrite the average value here, and then you can click on save and go next after that. So in the next slide, we are asked to calculate the mass. Yeah, so for that we have the weight, and we need to calculate the mass using the value of g. So the values in the previous slide, yeah, divided by g, 9.8 meter, you will get your mass. And put it there. Click on save and go next after that. While doing your experiment, your values might be different than what I have. Okay, so it can look different. I don't think that it should be fixed like bouncy ball. You might have a different size bouncy ball, yeah. Then based on that, you can have your weights. So it's not that you have to have what I have. Okay. Now we'll test our predictions here. We'll zero the without having anything here. Then you can click on zero sensor. Okay. Zero sensor. Then hold up bouncy ball approximately above 10 centimeter on the 4 sensor plate and record the height. Oh, so you can just hold around approximately 10 centimeter, or you can use the scale. Yeah? You can use the scale 10 centimeter. Centimeter this side, so you can say it has changed quite here. So you can hold it here around here, okay, and then you can write your height here. Say around 10 centimeter. You can use it, okay, and then click record and drop the ball so that it bounces straight off the table. So you can click on so of the plate. So the main thing is you have to make it hit here, okay. So it might not be possible in one trial. You can, so that's why we can add our trial remove, okay. Click on record, okay, and then hit it. Okay, I think I should have put this one, but okay, I can do it again. Okay, same thing around 10 centimeter. So after we are done, you can add on, and then without selecting anything here, you can click on zero sensor. Okay, to check if you can just record it without having anything there. It should be around 0 in here. This is overlapping, so we cannot see anything right now. And when it is finished, you can just click on zero sensor also, just to check whether it's 0 or not. Because when we had neither nothing, that the line has to be here, so it is overlapping, that's why it's not seen. Okay, so this one, this is I'm doing the second trial, okay, around 10 centimeter, and then click on record. Yeah, it has to be hit the plate, okay, and then you can see kind of this one. Yeah, so you can follow the trick and you can do the same thing. After that, we know to medium large plate, what is the maximum force exerted by the medium clip. After that, we have to do with the medium clay ball also, yeah, with the it is with the same height. Okay, so after that, for doing with the clay balls, those do not bounce, yeah. So you can spread a little bit of clay here, sticky clay here, okay, so that we have one to stick, but if it doesn't stick also, that's fine. But the idea is it has to stick, yeah. Then you can keep it here. So a small amount would be okay. The trick will be like we'll take this everything as 0 now, okay. So what you can do after that is we need a I've already done that. Then you can reach 0 sensor, okay. It has to be after putting thing, then you can leave 0 thing after putting this clay over here. And then let's do it for the medium clay ball first, yeah. Okay, after having the clays spread here and zeroing the sensor with that one in there, and then you can use your clay ball, yeah, from the same around 10 centimeter height. Leave it so that okay, it doesn't strike. It will be a usual problem, okay. By the way. Okay, so what we can do, we have not recorded, good thing. Okay, so let me start to record, and then you might have to give many trials, okay. Record it and then leave it, did it hit, kind of, but we can do it, but it kind of hit it, yeah. So I'm good with that also, but you can try, you can have many runs, okay. So if we are not satisfied, click on add run, Just 0 sensor. I have not selected anything. Okay, so 0 sensor. If you want to check on B, okay, that's fine. And then click on record also. And then okay, if I get this exactly. Okay, and okay, this one. That's actually good. Okay, so for you also you can do the same thing. Okay, so you can have many trials because you might not hit it in the center while doing. Okay, and then so maximum height. They are talking about the maximum height. Okay, so for that what you can do is, okay, let's see, because of that scale it might be difficult. Yeah, so you can say change, always change your scale. It's around 1 2. Okay, so let's do 3 minus 3 so that we can see clearly. Okay, I think last one is not what we want. So okay, maximum height is, we're talking about this one. Okay, somewhere around this one, but okay, after having like drop from the appropriate height, okay, for the bouncy ball, clay ball and medium clay ball similar to the weight of bouncy ball and the larger clay ball, I'm just showing you the expected graph. So okay, actually nature of the your graphs will be like this. So while measuring the maximum, oh sorry, I think I have not shared you here. So let me show you what I've done already. So while measuring the maximum height, you can see the maximum height. You will measure maximum height from this one. Okay, right here, right here. So if I want to share you, okay, so let me, if I, okay, this will be the one. Okay, this is what I already did. Okay, so this was with the bouncy ball. Okay, and that was with similar weight of clay ball, and that was with the weight of larger mass of the clay ball. Okay, okay, if you see here, so while measuring the maximum height, you can take the maximum height like the from the up to right around here. Okay, maximum height, that was for bouncy ball. Then you can measure this height, write it right in your, that as asked for the bouncy ball, and that is the maximum height for the. So what I'm showing you, what kind of graph you will expect for the bouncy ball. So it will be something like this, yeah. And the one with the clay ball, similar from dot from the similar height, similar weight, it should be around half of the weight. You see the weight is around half, yeah. And for larger clay ball, if I had exact double weight, like I had, it's not exactly double, it's like more than double. That's why I got the larger one. If it was exactly double to the bouncy ball, and from the same height it will be around same, but it's okay. I have larger, they didn't ask for just double, they asked for the larger one. So this is the kind of nature of the graph you will be expecting. Bouncy ball, clay ball with similar weight, okay, and measure the maximum height here, and write in your, fill this. Let me share the same thing now. Okay, okay, and then you can fill it here and click on save and go next. Yeah. Okay, in the next slide, did your observation agree with your prediction, which resulted in bigger maximum force, the bouncy clay bounce or ball or clay ball? So you already have the result, yeah. From that you can analyze. This one. So bigger force is of which one when you had? Okay, which one? So you can see that was bouncy ball, that was clay ball, like medium size and those things, yeah. So you can see which one had the larger one, okay. But that was bigger force, obviously, yeah, with the bouncy ball. So you can go ahead, write your answers. Okay, and then make your based on your graph, you can write your answers and then click on save and go next. Okay. So while throwing at the door, you will throw the one with the higher, what's it called? Higher force. Yeah. Okay. In the next slide, did your observations agree with their prediction? Oh, I think you did that. Yes, that one. So yeah, you can do the prediction. What will happen to the maximum force if you increase the mass of the clay ball? But oh, I think I have already. I showed the three graphs already. I did. Okay, let me show you. Okay, this was the one. What I'm trying to say is, Have I been sharing this one? Okay, I think I have to do this one first then. Okay, in this slide, so you have been asked to predict what happened to the maximum force if you increase the mass of the clay ball, but allow it to collide with the same velocity, so drop from the same height. Okay, so after that, I'll say the same one to explain. Okay, what I'm trying to say is like in the beginning you will have these two graphs only. Okay, that was for the other one which I already did. Like to get this one, you will use the bigger clay ball. Yeah, drop it from the same height for the third one. Okay, in the big for up to slide 7, you had these two graphs. We are making analysis on based on these two graphs. That was with the bouncy ball, and that was with the clay ball with the similar weight to the bouncy ball. Okay, we are dropping from around 10 centimeter for both of them, and then now we'll do it for. Okay, then we will increase the mass of we have to break the prediction. Okay, make the prediction. What happens when you increase the mass, and what will happen to the force if the velocity just before impact is increased by dropping? What will happen to the maximum force? And if you increase the mass of the velocity of clay ball, and the maximum of the velocity just before impact is increased by dropping the. Oh, so we can increase the like height and see the variation. Yeah. Okay, you can make a prediction and click on save and go next. Okay. Okay, then you can do the experiment. Yeah, so what you can do is re-zero the force sensor. As I have already said, you can click re-zero without having, we don't need the click, or you can put, oh, you're not seeing that one, yeah. This one, so where it is be, okay. So on here around, okay, okay. So I already have the clay, we can keep it so that the clay ball will stick. The main idea is that clay ball will not bounce off, yeah. And then re-zero the sensor, okay. Following the same process, you with this, I think we don't change the height. Similar with like previous around 10 centimeter, you can drop the clay, click on record, drop the clay ball, okay, get your graph, and then I'll show you later on, okay. And then within then measuring the medium clay ball. Now you use your medium clay ball, okay, the smaller one, but you'll drop on twice the arcs around like we're around dropping around 10 and we'll drop about 20 centimeter, okay. And why before doing both you can do this, like if you do the first one, record your thing, okay, and then click add on, then read your sensor, and based on that, okay, you can do based on that like that. Let me show you how what is the nature of graph you should expect. Okay, so the graph would be something like this. Okay, so what I'm saying is okay, so this was when I dropped the larger clay ball with from same height, and it was medium clay ball with double height. Okay, so by taking the maximum height, as I've said, you can take this side, it's equal to right negative sign. Okay, so for instance, for that around, you can use your tool, okay, in the IOLab, and minus it was 0 for in your graph section, and so it was around minus 8 point something for when I dropped. This is larger size clay ball dropped from around 10 centimeter height. That was medium size clay ball, okay, which was similar to the bouncy ball, dropped from higher, like double of the height. Okay, okay, let's. Okay, after that, based on your observation agree with your predictions, you can tell that what factors seem to determine the maximum force exerted on the force sensor. Okay, so what you can tell from that, from previous experiment when you had bouncy ball and clay ball, you can see the different what had, it was creating different force also, yeah. And in this case, if you see, we are using the clay ball by itself, okay. When the mass, when you change the mass and height, okay, the force can, the maximum force exerted can be changed. Like if the height is different, so there will be different in the velocity of with which the force sensor will be hit, okay, that will change. And with the mass also, because in this case you can see they had mass different, yeah, but we are still able to get the maximum force. So we can, by changing the velocity or drop from the height we drop, we can get different. Like in this experiment, the velocity is the one, okay. So or the from the height that we have dropped, we are able to generate say maximum force. So that mass and the velocity or the height also, okay. So based on your observations, you can make your predictions. Okay, you like write your answers and then click on save and go next. Okay. Okay, in the next one, so they are talking about the momentum change. Definition is given here. Okay, momentum is given by mass times velocity, and momentum change is final velocity minus initial velocity. So which object undergoes the momentum change during the collision with the door, the clay ball or the bouncy ball? Okay, and okay, so we have to do on that. I'm showing you what I have already done. So okay, so make your predictions. Okay, you can save and go next. Explain your reasoning. We already have the graph. Okay, and then okay, write your prediction and click on save and go next. Okay, after that is calculation time. Okay, so change the moment, calculate the initial momentum of the clay ball just before it hits the lap. So we already have the equation here, and the momentum is mass times velocity. So you have the mass, you have the velocity. So go ahead. If using this, you will find v, and then do mass times. What is the final momentum of the clay ball after it collides the IOLab? So it's going to stop. Yeah. So velocity is going to be 0. So mass times velocity will gives the final velocity momentum, which is going to be 0 here. Yeah. What is the change in the momentum? So final momentum minus initial momentum will give you the change in the moment. This is theoretical consideration. And just calculate the change of momentum in the bouncy ball from just before it hit the IOLab until after it bounces off, assume the bounces off. So the same velocity doesn't change. Okay. So same equation using b equals to 0. You'll find for the bouncy ball, find for the bouncy ball here. Okay. And the initial momentum is mass times velocity. And in the next one, mm, you will in the bouncy ball final velocity will not be 0. Okay, it's going to be same as the previous what's that called the initial velocity, but the sign will be in a different direction. Yeah, opposite sign. In the whatever you get velocity for the first one, take minus sign for the velocity while doing the calculation for final momentum. Okay, initial velocity is, if you take initial velocity as plus, minus is going to be final velocity is going to be minus. Okay, mass times velocity. So and the change of momentum is final velocity, final momentum minus initial momentum. Momentum are given by equation mass times velocity. Okay. Okay. Compare calculate change in linear predictions. Which object has larger momentum? So how does change in momentum be related to the maximum force applied to the ball? As in that time to okay. So you can go ahead write the answers. Okay. Okay, one thing as a reminder, they have due to arcs take positive y direction as upward direction. Okay, so if it's traveling in upward, velocity will be positive. If it's going downward travel, velocity will be negative. So if we are dropping the ball, so initial velocity is going downward. Yeah, so the velocity is going to be negative. So use v equals to g. Whatever you get value here, use minus sign over after that. Okay, so minus this value will be the initial velocity. Okay, finally 0 here for the second one. In the same this one, what is the change in momentum of the clay ball? So final minus initial, so you will have 0 minus so whatever initial momentum you have. Okay, and then same here, while coming down you use same equation, b equals right root 2 gh, but use minus sign for the initial velocity. Okay, since it's coming down and we are taking upward as the positive direction, and while going up you positive for the final velocity you can keep the positive sign, and then compare calculated change in momentum to your prediction. So you can see based on what did you predict, which will have the higher momentum, or previous slide. Okay, all those answers. How does the change in momentum seem to be related to the maximum force? If you have maximum force, the change in there this will be directly related, yeah, directly proportional, something like that. Okay, higher the change in momentum, higher the maximum force applied will be to the ball. So go ahead, write your answers based on your. And see if I need to remind you something somewhere. I think which objects undergo momentum change. Yeah, you can find last one, this one. Don't worry about that graph. Okay, that's not right, but okay, this one, mass and velocity. I already said that. Yeah, mass and velocity seems to are the factors that will determine the maximum force exerted. Okay, okay, we are on this slide. After that, you may go ahead, write your answers, and click on save and go next. Okay, don't forget to write the answers. I'm just okay. Is it prediction time again? Okay, so I think based on what we have done, they will be asking the question now. Okay, in this slide, so if somebody throws egg at you, so you have to catch it without being big. So you'll have a small time delta t or large time delta t. We are asking, we are being asked that. Yeah, so we already know force is rate of change of momentum. Yeah, from somewhere. So if rate of change of momentum is constant, so we need to catch it with a smaller force. Okay, so if you Force is rate of change of momentum. So del p by del t. If you have constant del p, and if you make del t small, okay, in that case force is going to be large, because if you divide something by smaller, it's going to be larger value, yeah. And if you divide something by larger value, you have a smaller. So in order to avoid the egg from breaking, we'll use large force, and because like if you use large force, the small force is applied while catching the egg, okay. And then yeah, if we use higher time interval while oh sorry, if we use smaller time interval while catching the egg, higher average force will be exerted on the egg that will break the egg, okay. So it's better to use yeah, the larger time. So that's why we pull our hand to create the impulse, sorry, it's momentum change, yeah. So that a smaller force will be applied, average smaller force will be applied. Okay, you can write your answers and then click on save and go next. Write your answers. Okay, I'm not writing, I don't need it now. So momentum change, and okay, so I think they have explained here is one force change in momentum, so you can go ahead. That is what I have already said, okay. Force times delta t is the area of the impulse, something like that. Okay, to clear the previous concept, as we say, we always have the like same momentum while whether we catch with in shorter time or larger time, yeah. So so impulse is given by the force times f times delta, yeah. So impulse is same, okay, we have to get the same area. So if we increase delta, so the force is like, if we make it, if we stretch it here, okay, it's going to be like the area, in order to keep the area same, the force is going to go down, yeah. But if you want to decrease the time, if we decrease this part, so like for delta is something around here, so for this, for like to cover up this one, we have to add this here, so higher force have to be applied, okay, because changing momentum is going to be same. If we increase the time, so if we increase the time, so like if you have to fill this area, okay, so we can take something from here, fill it here, that will decrease the force, the average force is decreased. But if we decrease the time, delta t is small, okay, so we have to cover it for this one on this part of the, if I keep delta t here, I have to cover this one, that's going to go up, so higher force will be applied, that will break the, okay. So delta t has to be larger to avoid egg from breaking. Okay, next one, impulse, momentum and collision. So make sure you write your answers, okay. I'm just showing in and moving forward. At the spring and the screw, place the eyelab so that the wheels are on a smooth. So you already have this one, yeah. So you can have the, oh sorry, now you need to use the spring, very good. Oh sorry, I've got something from the eyelab thing, yeah. And this works. So you have one with the spring, this one, okay, something like that. You might have got this one, and then you can take, you don't need this now, you can take this one out, screw it out, okay, and place the one with this screw. You can pause it now, we don't need it. Okay, so let me see how time is here and is that thing, okay. So if friction is negligible, what is the net force? Let's you can do this, place the lab so that the wheels are, actually I have already got placed with this spring, yeah. Okay, on this spring. So you can place it like this. Okay. And if the friction is negligible, what is the net force exerted on the eyelab just before it starts to collide? So net force before collide, there is no force being applied here, yeah, before collision in this one, so that would be zero. Obviously, you can go ahead, make a prediction. What is the net force on the card maximum? So you can make a prediction before it is touching the switch on the wall, or it should be when it is compressed fully and ready to come back, that should be the maximum force. But go ahead, read and make a prediction, you will see it later on, yeah. How long does the collision takes for it? Should not be like if you just click it like this, so collision time should not be that much, okay. So make your predictions, write your answers, and click on save and go next. Okay, so collision change time, predict, this is prediction again. So what kind of graph do you expect force times delta is here. Yeah, so what kind of one do you expect is force times delta t? So obviously we have already seen we will not get exactly same like this. Yeah, like it's not possible while doing the experiment. These things. Okay, so go ahead, make your predictions. Okay, so while doing the prediction, okay, force versus the time. Okay, so what is asking is how much force is exerted on the IOLab by the wall during the collision, okay, as a function of time during the collision, okay. This on the IOLab, be sure of that, okay. So when it is going there, okay, so that's the time of the collision, yeah. Goes up, that's the time of the collision, okay. So that side is positive y-axis, obviously, and we are moving from double L to single L. So this side is positive y-axis, okay. But when it's going to hit here, while this, what's it called? Will be applying the force. While is applying the force on this one, yeah. If it's going it one, it's trying to stop, so the force has to be applied this side. Releasing, the force is going applied in that side. Okay, so let's see. Negative side. So obviously velocity while going this. Okay, and they have given how can we plot of force versus time. If we find area under the curve, that will give the momentum. Okay, measure the velocity of the car before and after the collision with the wall. Okay, that's what we are trying to do. IOLab, we can do it with the IOLab. Okay, then after that make a prediction, click on save and go next. Okay, time to do the experiment. Okay, that's out. So I attach this, we already did that, yeah. Lab force sensor, make sure the force sensor is calibrated, or you don't need to do that if you have done it already. Pull the IOLab table with the spring pointing upward, like you can do it something like this, and then click on re-zero sensor. Okay, and now click the record and lift the IOLab by click the record and keep it steady. Do not let it swing after a few seconds. Click on this. Let me hold on. Okay, they're trying to find the weight of the IOLab. So they have asked, let us lift the IOLab. So click on record. Just click on record. You can lift the IOLab. Okay, let me do it again. I think I missed it. But if you don't want to do that, that's the area of the interest when I lifted it. Yeah. So I can do that again. So it's not a problem. Then record it. Oh no. Okay, I can just read the sensor. Record the lab. Keep it steady. Do not let it after physics. Like we don't need. Yeah, after the average weight. While it was hanging. So you have to be quick. Record it. Lift it. Keep it steady. Then you can read it. Then you can find the average weight recorded over the few seconds, so you can do the average here. Just making selection, like I have not lifted it here. Yeah, I lifted it here, so you can do the average here using this tool. Okay, over here use the formula weight equals mass times gravity to calculate the mass. So we have we got the weight, so mass is going to be weight by g. It's 9.8. Okay, then you can place the IOLab on this about aimed at about 20 centimeter from the wall, so they don't want it that much, so just around 20 centimeter, yeah, from the wall. Can you see it? Okay. Click on record, give the IOLab. Click on record, give the IOLab a push, click stop after the IOLab bounces back from the wall. So let's do it. Okay, without nothing on the IOLab, we can re-zero the sensor. Let's, where is that come? Okay, it's turned off. Okay, so already. No, I have to add one. It's better to add one. V0 sensor around 20 centimeter from the wall. Okay, record, give the eyelab push, kick it after the bounce it from the wall. So record, give it to push. Oh, that's not good. Okay, no. Okay, I'm going to zero the sensor. Yeah, then click on record, give it a push. They ask you to stop, but we don't need to. Yeah, it will stop by itself. That's okay. Okay, after that, I think we already this. You can fill this one. Okay, with your equation and the value from here. Take the average. I'm not filling it, but make sure you fill it before you click on save and go next. Okay, and then you can click on save and go next. So does the shape of the force agree with your prediction, or you already predicted in the last one? Click and drag across the last peak in the force graph on the other end of the graph, and the graph line simple. It will be labeled at A. So above the force and graph, I want it. Okay, following the instruction. I think we don't need the video, so let me take it out. Okay, I think we don't need the video after with that one. So we have to. They want you to select the peak of in the force graph. Yeah, we have to find the area of this one. So we already have this tool. So you just make sure you start from here and up to the peak only. Okay, so there might be some. Okay, so you see, it's just selecting the area in the peak in the book. So force is area under the crop. So you labeled as A. So you can so is the label. So that's the of the interest. Yeah. So you can see the area is here, the bottom one. Okay, be careful with that. Not use the top one is for the top this graph. We are not doing that right now. This is this area, so that's the area under the crop. You can write the value here. Move the cursor so the line appears at the left. So we have to consider doing the same with the same line. Okay, so we will be considering the velocity here and here. So you can get the velocity from here just before collision. That's just after collision. Yeah, so just before collision, velocity is here. So where is V? Find it V. Okay, so in this one actually, so that's going to be 0.32 something. Yeah, and the next one velocity is after 0 point minus I said around, okay, just before collision and after collision minus 0.24 if it's here, as after collision, before collision 0.32. So you can write your values here, final velocity, initial velocity with the sign. Okay, change in momentum is final momentum minus initial momentum. Mass times velocity will give the momentum. So mass times velocity got here, mass we got from the last slide. Yeah, mass times final velocity minus mass times initial velocity. So initial velocity is positive here, final velocity is negative here. So then you're using the equation, delta p is final momentum minus initial momentum, final momentum mass times velocity, final velocity initial momentum mass times initial velocity. Okay, here's the equation. Get your answer, write your answer and click on save next. Okay, I'm just doing it directly. Okay, so did the calculated magnitude of so area of the momentum implied to the wall during the momentum change in momentum IOLab equal the magnitude measure impulse applied to the wall. So they are asking, so what you got from the calculated value, is it equal to the area what you got impulse thing? Yeah, you can explain. Now after that they are trying to predict what would impulse we find. What would the impulse be if the final momentum of the IOLab were larger? If the final momentum were larger, change my it's going to be larger. Yeah, so this is prediction. You will find out in the following activity. When you do the next one, we'll find it out, but you can just go ahead and predict. If we increase the final velocity, so it's in the higher side, it should increase obviously. Yeah, but we'll see. Okay, we'll see what happens, and then momentum. uh, okay, here the momentum are in same direction. Yeah, mass times velocity, mass times, sorry. Okay, after that change in momentum, you can click on save and go next. Okay, so what is being asked, let's see. That is turned off, so that's why we don't have the IOLab. IOLab object of mass approximately equal to the IOLab or collection of coins or the small mass at the coin box that IOLab came in, or the small paper clip, scotch tape, screw with the spring. So we already have this screw with this spring. Okay, I'll just suggest what you can do. Okay, So we'll have a screw with the spring here. Okay, and then we need a mass that is equal to the IOLab, so you can uh, use it with the box that came from with the IOLab, put some coins in it and try to make it equal to the mass of the IOLab. Okay, you can assemble the mass of the IOLab. We already did that. Resonance is calibrated. All the IOLab with screw eye pointing. All the IOLab with this guy pointing down and zero the sensor. So what they are trying to say, they want you to do like this. Okay, how you can do it? Okay, so then zero the sensor. Okay. Mm. hang the box from the Hang the box from the sky and add mass to the box until it's weight about the same as the IOLab. So in measured in activity 2.2. So we already measured the mass of activity 2.2. What is that activity 2.2? We already did that. Okay, I think we did that, but activity 2.2. Oh, we have it here, yeah, mass of the IOLab. So we will make equal to that IOLab. So what they're trying to say is like you can keep something in the box or you can use water bottle also. It's up to you. Okay, and then you will hang it like this way and make the weight like for will make the weight equal to whatever you had in activity 2.2, and that will be equal to the mass of the lab. Okay, and then you write answer, click and save and go next. For now I'm just clicking it. Okay, tape the box with the mass. Okay, so after that what you will do is you'll tape it here. Okay, you can tape with the lab. Okay, so that will now we have a double mass here. Make sure the screw with this. So while taping it, don't do it like this way so that the screw cannot hit. Okay, so do it something like this way. Okay, on the top, screw it, and so that if we do it like do it, while pushing it so that the spring can hit the screw wall. Okay, with that, calculate the ala with the wall again several times until you get the initial velocity about the same as in activity 2.2. Okay, final velocity. Find the velocity as oh, so we have to be careful. So what they are trying to say is like you can say while pushing you can change the force here, like with which you push. So what we had in the activity 2.2 is already you already know how much is that. Yes, okay, initial velocity was around 0.33236, yeah, 32, yeah, 0.2832, yeah, you can see it just initially before collision. So that's around 0.32 to 0.28, you can better after that. So you will give the push. Okay, well, with the weights on double weight you can give the push, and you can with the same concept here, yeah, you can see the initial velocity of the eyelab, final velocity of the eyelab in that slide also. Okay, and what they want you to do is like you have to make the value of the initial velocity same around 0.3. Okay, like 32 is 0.3. Okay, so you can push the eyelab, get the value equal nearly equal to the other one. Okay, so velocity toward the wall, again so using the same concept, they want us to be straight. For velocity away from the wall, you will see how much it will be. Okay, and initial velocity about the same as in activity. You find the velocities in activity as in activity 2 and calculate the change in momentum. So same concept here, mass times velocity, we can do that. VF is just before the collision. VF is just after the collision. Final velocity is just after the collision. Initial velocity is just before the collision. Okay, VF, final velocity, initial velocity here, final velocity here. Okay. Don't take it that's exactly there, just before the collision means right here, around here, and right around here. Okay, and then with using this you can change, you can calculate the change in momentum. Yeah, initial momentum you can do that. And remember that direction away from the wall is positive, so and towards the wall is negative, so be away from that. Always like this side is away from the wall, this side is positive. Okay, that side is negative. Okay, surprise, but okay, and then don't get confused about the sign. Okay, so whatever you get from during the experiment, you can write that like here. This is velocity, this is toward the wall, yeah. So positive sign you can take it, this is positive you can see, and for this one that's negative sign. So don't get confused and write your answers. mm, so that's going to be positive, that's going to be negative here, okay. Value here, so you same, you can get the initial and final ones, mass times velocity minus mass times velocity, yeah. Then the momentum, mass times initial velocity gives initial momentum, final mass times final velocity, final momentum. So that is final momentum minus initial momentum. And then impulse, from the graph you have to select the area of that same thing, yeah, like we did the last one, okay. The area here, okay. 21. mm, and then you can click on save and go next after you're done. Okay, did the impulse agree with your prediction? You can answer that. Where the impulse and sensing momentum equal to each other, they have to be, they will be around equal to each other, yeah. And while explaining, we already know force is rate of change of momentum, yeah. So F equals del P over del T, and if you do F times del T, so you can already see del P, change in momentum, is equals force times del T, which is impulse, yeah. So you can just write your answers based on that, and then you can go click on save and go next after writing the answers. Okay, don't forget to write the answers. I'm just clicking it for now. Okay, what would be the impulse if the collision were inelastic rather than elastic? What if the, okay, so go ahead. We have to make the predictions now. Okay, so we have been asked if the elastic were collision, what would happen? What would be the impulse? Okay, so if everything is same and the collision is elastic, is it the impulse larger or is it elastic? Like when we collide with the wall, it's going to stop. Okay, like it is not going to bounce back. That's the whole idea. So because you can make a prediction, but since there will be no contribution from the final momentum, so I think it's going to be smaller, but you can make a prediction. Okay, so what will be screw with the plate, large block clay, small piece of clay, and thumb stack. Okay, so after remove the string. So I think I already did that. I removed the string. Okay, I removed the string and I used this was a screw plate. Yeah, and then I put some clay on that and some thumb pin. Like you can use the thumb pin, regular thumb pin, so that you can stuck it in the clay so that it is stuck here. Okay. I have luckily I had the one with the hook kind of hook thing, but if you don't have the hook also you can what's that called with the clay, it will stuck here. And so wherever you are hitting, okay, on the wall, put sorry, okay, put some clay ball, or you can use the big ball also. Okay, I didn't need the big ball, so I just used it one. And I think we have been asked to leave the mask there. I have not used it. So the mask you used, it was around IOLab, yeah, just keep it here. And you have to be careful, it should allow you to hit there. The mask will not come in between. So you can, before, just before this one, plus the mask before this one. So we cannot, okay, so what do you predict about the impulse and momentum? Will now the card hits the wall and it comes to race. What do you predict about the impulse? So I said that, yeah, if you find momentum is not continuing, what do you predict now about the impulse and changing? Will they be equal to each other or will one be larger or what? Okay, so go ahead, that's pretty easily. So you can write your predictions and click on save and go next. Okay, that's already on. Click on it on. Your IOLab will be on if it is inactive for some time. Yeah. So reserve the film sensor, collide the current until initial velocity. So we have to get the initial velocity same as before. Okay. So let's click on the sensor, doing the experiment again. You can close it here. Make sure you don't hit other things. So I'll just give the general idea of the graph. Okay, how it look like. So you can click on record, and if I give the push, you see it is stuck there. Yeah. Okay, I think we wanted to. So the thing was I was trying to say the velocity will be zero. Okay, that was the one I was trying to say, but I can do it again. Mm. If we actually do the experiment, so this is let's go ahead with it. Mm. Okay, so the activity will have something like this. Yeah, with the thing already. So the clay, you can use the thumb in here. Okay, make it straight. Okay, so that and then you have the clay ball here. it collide it from here, and you just do it like this way. Okay, so while recording, what you with the thumb stick here, what the intention is, you will go there, it will just collide and stuff here. Okay, and then okay, let me show you the graph. Let's say okay. Yeah, okay. So this one, okay, so this will be something like this. This one now. So you see, if you decide with velocity and when it goes there, this kind of velocity will be zero. Yeah, there is no final velocity since that will be stuck. The eyelab will be stuck in the wall, and then the momentum you see this delta t. So let's say the difference. Okay. So your answer will be different. Okay, like it might be here might be within different velocity and different. So you see, it was kind of flat here, and the time was delta t was longer. You see, and in the next one when we did, this was for when we didn't we just had the string. Okay, not it was elastic collision. This thing you say you had final velocity and initial velocity both. Yeah, but in the next one, if you share, you only have the initial velocity and final velocity, and you can see the difference. Delta is smaller. That's why area. Okay, you see. And we have to strike with the same velocity in initial velocity that it was in the elastic collision. Okay. And then okay, the next one. Alright, okay. So click on 7, go next after that. Okay. Okay. So compare the force time for inelastic collision to that of nearly elastic collision. How are they similar and how are they different? I already said. You can see that delta is different. Yeah, the delta is different. Where the impulse change in momentum equals same. You can say that. Okay. Did I do 24? Hold on. Okay, let me see. Did I skip one slide? No, this measuring thing, you can do that. Yeah. Velocity toward the wall, velocity away from the wall is going to be zero because it's going to stop. And then same formula, initial momentum minus final momentum from the over the impulse thing. Okay, we can go ahead and do those things. And then next one, slide 25, this is the last one. Okay, so, so what we have been asked for is compare the force time for the elastic collision, time for the elastic collision. Okay, how are they similar? Are they different? For instance, both have similar shape is similar. Yeah, you could have seen the same shape is similar. Let me see if I can share that one with you. So, okay, okay. So you can see the shape is like for both of them. It is similar. Yeah, if you see the shape, you see the shape is same similar. The graph of the same is similar. So only the delta t is changing. So next thing is kind of thick. Okay. Okay, yeah, so that one, only the impact time was different, right? Impact time was different, shape of the graph was different, where the impulse and change in momentum equal to each other for elastic cooling. Yeah, they are same. The impulse and change in momentum, we already did that, yeah. So it's always same. The momentum change is equal to the impulse power collision. So I think that's on what we have. We had seen for elastic collision and elastic collision as well. So both both can be same. Yeah? So it for elastic collision, change in momentum and impulse are same. For in elastic collision also we have seen the same thing here. So they can be same. That's for sure. So change in momentum and impulse can be equal in both the cases, elastic collision and elastic collision. Like we separate during the elastic collision also impulse and change in momentum are same. During the elastic collisions also when we did that change they were same. Impulse and change in momentum equal each other. Clever, do you answer so one and three? Anything, yeah, if we have the clay ball and bouncy ball of the same What's the mass? We would like to use the bouncy ball to throw, yeah, to throw to the ball. Yeah, yeah, bouncy ball, you are getting what's it called? Elastic collaring, yeah, and then so that you will have the force acting on the door for the longer time, and then so that's why we'll prefer bouncy ball thing. So instead of the play ball, it's yeah, and then the right answer is okay. Finally, it's like the video I'm making is all instructional. Okay, so don't you can follow the nature of the graph, but don't follow try to have the exact answer. You might have a different size of the clay ball, different mass of the clay ball, different mass of the bouncy ball. Okay, so but make sure that you get the concept and the nature of the graph are pretty similar. So way to measure, you have to be careful with that because I have seen instance measuring whole of the graph. We don't need that. Okay, it is the exact part that we are interested in or the problem asks first. Everything is running, so click and save and then that will be the final. Thank you all.